Hello everyone, myself Yalini from the Department of Computer Science and Business System in Ramco Institute of Technology. Today going to see about data structure and design in AVL Tree. So now we are going to see about AVL Tree. AVL Tree is nothing but Adelson, Wolski and Landis. Adelson, Wolski and Landis. It's a self-balancing binary search tree. The AVL tree is same as that of binary search tree, but here we are going to consider the balance factor. The balance factor must be range between -1, 0 and +1. We are going to find out the balance factor by using the formula height of left subtree minus height of right subtree. For each and every node you have to find out the balance factor. If the balance factor not range between -1, 0 and +1, that tree is said to be imbalanced AVL tree. Let us see an example of imbalanced AVL tree. Here we are going to find out the balance factor. The balance factor of 3 is there is no left and right child node, so 0 minus 0 is 0. Here 5 for the same balance factor is 0. For 4 the balance factor is left subtree is 1, right subtree is height is 1, so 1 minus 1 is 0. Here the balance factor is 0. Here the balance factor is 1 and height of the left subtree, right subtree is 2, so 1 minus 2 is -1. Here it considered to be a balanced. Here 8 is considered to be balanced. Here there is no right and left child, so 0 minus 0 is 0. So you have to find out the balance factor of 6. Here you have to consider the highest depth, which will be the highest depth is considered as height. You didn't consider here instead of this because here you have to consider the highest depth. So 1, 2, 3. So height of the left subtree is 3. 3 minus 1 is 2. So other than -1, 1, 0 means that tree is said to be imbalanced tree. So while inserting every nodes, you have to check the balanced factor. If the tree is said to be balanced, the range between -1, 0 and 1, other than this, that tree is said to be imbalanced. If it is imbalanced, you have to do the rotation. There are 4 kinds of rotation are there. Okay, let's see this with a simple example. Let's see this with a simple example. Here the set of elements are given. You have to construct an AVL tree with the given set of elements. First, the insertion could be done as same as that of binary search tree, but here we are going to check about the balance factor also. Okay, first insert the element 1 and check the balance factor. It got balanced. Then insert the element 2. 2 must be greater than 1, so insert is as the right node of 1. Now check the balance factor. It got balanced. Now insert the element 3. 3 must be greater than 2, so it considers as a right node of 3. Okay, so right node of 3 means now check the balance factor. Here 0, it got balanced. Here it is 0 minus 1, it got balanced. But here there is no left node, so 0 minus 1, 2. So minus 2 occurs here. So the tree considered here as imbalanced. If it is imbalanced, you have to point out the position of the child nodes, that is it is right position of subtree is happened here. If it is r happened means you have to rotate the right node, that is root node, towards left. Okay, if it is RR means you have to rotate the node towards left. So the tree must be like this. If you are going to rotate the tree like this, 1 comes to the left node and 2 will be the root node and 3 will be the right, same as of 2. Okay, now insert the element 4. 4 must be entered here. Now check the balance factor. 4 is balanced. 3 is 0 minus 1 is balanced. Then 1 is balanced. Then 2 is balanced. Then insert the element 5. If you are going to insert the element 5 here, after 5 must be greater than 4. So after 4, right node 5 will be the right node. Then choose the check the balance factor here. It got balanced. It got balanced. Now here one more point you have to be noted means, that is you have to check the balance factor from the leaf node to root node. Okay, then only we have to find out the pivot element where the imbalancing occurs. Okay, here the 3 must be the imbalance existing node, because here the balance factor is -2. Here no left node is happening. Here 2 right node is here. So 0 minus 2 is -2. Here the imbalancing occurs. If imbalancing occurs, you have to find out the position of subtrees. That is, here arise R. So right. If it is a right rotation, means you have to rotate the tree towards left. Okay, if it is RR rotation, means you have to rotate the root node towards left. Okay, so after rotation, the tree will become like this. Now check the balance factor. The tree got balanced. It is 0, it is 0, it is 1 minus 1, 0, it is 0, it is 1 minus 2 minus 1. So the tree is said to be balanced. Then finally insert the element 6. Okay, you have to insert the element 6. 6 must be greater than 5. So it will be considered as a right node of 5. Now check the balance factor. It is 0, it got balanced. It is 0 minus 1 minus 1, it got balanced. It is 0 balanced. Now check the balance factor of 4. 1 minus 2. So here the balance, sorry, it got balanced, -1. Then check the value of root node balancing factor. Here it is 1 minus 1, 2, 3. Why we consider this instead of this? Because you have to take the highest depth. Is that so? So 1 minus 3 is -2. Here it is imbalanced. If the imbalancing occurs, you have to choose the position. Here there are two kind of position, R and L, R and R. Is that so? So R and L and R and R. So R irukku, R L irukku. Here we are going to choose RR position. Why we choose this means this will be the maximum height test, maximum depth. Okay, so you have to choose the maximum depth. So RR rotation means you have to rotate the root node towards left. So 2 come as a left sub node, then 4 will come to a root position. 5 and 6 will be in same position of right subtree of 4. So அதே same position la 4, 5, 6 arise ஆயிடுச்சு. Then 2 should be a left node of 4. இங்கே ஒரு element இருக்கா? Here one element is there, that is 3. So 3 will be the left node of 4. So 3 should be in the position of left of 4. இங்கே பார்த்தா that is already 2 is there. So you have to compare the element 3 and 2. So compare பண்றப்ப 2 must be smaller. So 2 must be smaller நால make the element 3 as a right subnode of 2. So now check the balancing factor. It got balanced. Okay, just make it as a point. If it is R means you have to rotate the tree towards left. If it is L means you have to rotate the tree towards right. Just keep it in mind. Okay, now see this with another example. So there are 4 kinds of rotation are there, that is LL rotation, RR rotation, LR rotation and RL rotation. So I will explain it with a simple example. If I will explain it with an example means you will understand more clear. Okay, so these are the set of nodes. These are the set of nodes given to construct an AVL tree. The first element is 63. So 63 is considered as a root node. So root node, you have to check the balance factor of 63. Here the balance factor of 63 is 0. Now insert the element 9. 9 must be less than 63. If the element is less than 63 means you have to insert the element into left. If it is greater means you have to insert into right. Okay, so 63, 9 must be smaller than 63. So insert into left. Now check the balancing factor. Here 0, here 1 minus 0 is 1. So here it is balanced. Now insert the element 19. So here 19 means it must be smaller than 63. So it comes to the left node, it must be greater than 9. So the element here is 19. So now check the rotation here. It is LR rotation. If it is LR rotation means just make it a note. If it is LR rotation means you have to rotate the child node towards left first. You have to, if it is LR means you have to rotate the child node towards left first, then pivot node, root node towards right next. So the two rotations are happen here. LR means first rotate the child node towards left, then rotate the root node towards right. Okay, so after first rotation here 19 is the child node. Here you have to rotate the child node towards left. So LR means towards left. So if we rotate the 19 towards left, the tree will come like this. 19 will come to a middle and 9 move on to left node, then 63 is same as that of root node. After first rotation, you have to rotate the 63, rotate the root node towards root element, pivot element towards right. So after it rotate into right, this element come to a right node and 19 will come as a root node. So the tree will come like this. Okay, or you understand, if it is LR rotation means you have to move the child node first towards left, then root node next towards the right. Okay, is the same condition for RL also. RL means what you're going to do. If it is RL, you have to rotate the child node towards right first, then pivot element to left. Okay, so now check the balance factor. It got balanced. Then you are going to insert the element 27. Now check the balance factor. Here 27 must be lesser than 63. So it should be the left node of 63. So it got balanced. Now check the element of 18. 18 must be lesser than 19. So it comes to the left node. 18 must be greater than 9. So it comes to the right node. Now check the balance factor. Here 0, here 0, here minus 0, minus 1, minus 1. Here 0, minus 1, minus 1. Here 1, 2. Here 1, 2. So 2 minus 2 is 0. 18 is balanced. Now insert the element 108. 108 must be greater than 19. So come to right. 63. So come greater than 63. So come to right. So insert here as 108. Now check the balance factor here. Here the balance factor is 0, 0. All got balanced. Now move on to next. Okay. Okay, fine. So coming to the next insertion is 120. 120 is greater than 108. So it should become like this. Now check the balance factor. These and all got balanced. The root node is 1 and 2. You have to take the greatest, the deepest height. Is that so? So deepest depth. So 1, 2, 3. So 2 minus 3 is minus 1. So it is also got balanced. Now finally you are going to insert 115. Okay. So you are going to insert 115. 115 must be smaller than 120. So it should be the left node of 120. Now check the balance factor. Here 0. Here 0 minus 1 is minus 1. Here the balance factor is 0 minus 2. So minus 2. Here the imbalancing occur. So you have to choose the pivot element. Pivot element is 108. Okay. So pivot element is the root element. So you have to do the rotation. Here the position is R and L. So RL means what is the condition? You have to R and L means you have to move the child node towards right, then pivot node towards left. Is that so? So you have to move the child node towards, you have to move the child node towards right. So while rotating the child node towards right, this 115 and 120 becomes like this. 115 came here and 120 moved to the leaf position, then 108. After completing this kind of child rotation, move on to the root rotation. Root rotation towards left. So 108 came here, 115 come as a root node, then the tree will become like this. This is your final tree. Now check the balancing factor. It got balanced. 0, 0, it is 0, it is 0, it is 0. 0 minus 1 minus 1. Here 1 minus 2 minus 1. Here 2 minus 3 minus 1. So the final complete balancing tree is achieved. So this is the condition of AVL tree. So in this AVL tree, you have to keep in mind as left rotation means rotate the pivot element to right. Right means rotate the pivot element to left. Left right means rotate the child to left first, then pivot to right. Okay. If RL means you have to rotate the child to right, then pivot to left. That's it. So that is a thing about AVL tree. This is same as that of binary search tree, but the rotation is, if the rotation happens, it is same as that. It is occurred in AVL tree. So AVL tree is considered as a self-balancing binary search tree. If you have any doubts, you can ask in comment section. I will make it clear. Thank you.